In this video, we're going to talk about cylindrical and spherical coordinates. Now, let's recall that in 2 space we have both rectangular coordinates, x comma y, and polar coordinates, r, theta. And we can convert back and forth between rectangular coordinates and polar coordinates. And we've talked about that before. Now, in 3 space, we are going to look at 3 different coordinate systems. First of all, we have rectangular coordinates, and we've already seen this here. This is x comma y comma z. So if you have a point out here in 3 space, you can describe where that point is by saying how far you're going out along the x-axis. So it looks like maybe they're going out 1, 2, maybe about 3 along the x-axis. And then how far in the y direction, looks like it's maybe 1, 2, 3, 4 or so in the y direction. And then how far up? Okay, maybe it's a height of 5 here or something. So maybe it's 3 comma 4 comma 5. Okay, that's how you describe where a point is. Okay, how far out along the x-axis in the x direction, and in the y direction, the z direction. And again, it kind of looks like a rectangular box, so this is called rectangular coordinates. Okay, now we could also describe where a point is by, so a point in 3 space, by dropping that point down into the xy plane. And then within the xy plane, of course, you could have an x-coordinate and a y-coordinate, but you could also have an r and a theta, right? The polar coordinates of that point. So the cylindrical coordinates of a point are just the polar coordinates, right? R, theta, once you've dropped it down into the xy plane, but then you also attach the z-coordinate. Okay, so you drop this down to the xy plane, or actually if z is negative, you bring it up into the xy plane. But the z is just the z coordinate, okay, of the same as the rectangular coordinates. But the r and the theta are really the polar coordinates of that point once you've put it into the xy plane, projected into the xy plane. Okay, so cylindrical coordinates are kind of like the 3-dimensional analog of the idea of polar coordinates. Okay, now the really new system then that we're going to deal with is spherical coordinates. Okay, so what's another way that you could describe where a point is in 3-dimensional space? Now, another way to do this would be to say, well, how far away is the point from the origin? Okay, and that will be rho. Now, notice that's different than r here. This point is not at a distance of r away from the origin. This point is at a distance of rho, is what we're calling it, from the origin. Now, let's suppose that we've nailed down what the rho is. So maybe like rho is 5. Okay, so how many points are at a distance of 5 away from the origin? Well, there's lots of them. In fact, they would all lie along a sphere. In fact, that's why we call this spherical coordinates here. All the points that are 5 away from the origin will lie along a sphere. Now, so if we want to just nail down one point, just giving the rho is not going to be enough. So how can we also say where that point is? Well, another way of doing this would be to, again, drop this point down into the xy plane, or if it's below the x-axis, bring it up. Okay, do a projection into the xy plane, and then figure out what this theta would be. Okay, now once we've nailed down the rho and the theta, that's still not quite enough. In fact, it's a little tricky to visualize here, but if you specify a theta, maybe the theta is, let's say, 30 degrees, okay, and the rho is 5, well, that still won't be enough. You'll have lots of points. They'll all lie along a circle. In fact, really a semicircle, because the other side of the circle, instead of being 30 degrees, it'd be like 210 degrees would be the theta over there. Okay, but you're really getting a semicircle. So how can you nail down where on that semicircle you are if you have the rho and the theta? Well, that's where this phi comes into place. Okay, so this is a Greek letter phi here. So the phi really just tells you, if you draw the line segment from that point to the origin and figure out what the angle is that makes with respect to the z-axis, the positive part of the z-axis, that angle will be phi. And then once you've given that phi, you've found where that point is in 3 space. Okay, so you've found uniquely where that point is. So once you have a rho, a theta, and a phi, that tells you where the point is. Okay, so we have these 3 different systems. Now we'd like to be able to convert back and forth between the 3 systems. Okay, so how do we do that? Well, we're going to have all these formulas, and this probably looks crazy, and you think, how in the world am I ever going to remember all these formulas here? But actually, in the top 2 rows here, cylindrical to rectangular and rectangular to cylindrical, right? Converting back and forth between these, we already know how to do that, because that's just like converting back and forth between rectangular coordinates in 2 space and polar coordinates. In fact, if we're given a r, theta, and z, how do we come up with the x, y, and z? Well, the z will just be z, but the x will be r cosine theta, and the y will be r sine theta, right? So we've already seen that. Okay, and similarly, if we're given the x, y, and z, how do we come up with the r, theta, and z? Well, again, the z is just z, and then the r is the square root of x squared plus y squared, right? And the tangent of theta is y over x. Okay, so that gives you theta, right? Theta is tangent inverse of y over x. Okay, so we already know how to convert back and forth between these two systems. Okay, so really the new one is spherical. So how do we convert from rectangular to spherical and back? And how do we convert from cylindrical to spherical and back? So let's do this last one. How do we convert back and forth between cylindrical coordinates and spherical coordinates? Okay, and just as a note down here, I already mentioned this. If you know how to convert back and forth between rectangular coordinates x, y and polar coordinates r, theta in 2 space, then you already know how to convert back and forth between rectangular coordinates x, y, z and cylindrical coordinates r, theta, z in 3 space. Okay, so let's talk about how we convert from these cylindrical coordinates to spherical coordinates. So if we're given the r, theta, and z, how do we come up with the rho, theta, and phi? Well, notice the theta is the same in both cases here. The theta is just equal to theta. Now, the key thing is I'm going to draw this picture, and this picture really is all 3 of these combined at once. Okay, so I'm drawing in the x and the y and the z, and I'm also drawing in the theta and the r and the rho. So I'm putting all these in the same graph here. Okay, so how do we find how do we find theta in terms of these? Well, theta is theta. How do we find rho in terms of these coordinates? Well, notice that if we draw this little triangle here, this right triangle here, that rho squared will equal r squared plus z squared, right? Because rho is the hypotenuse. So rho will be the square root of r squared plus z squared. So we've written rho in terms of these 3 coordinates here. Rho is just the square root of r squared plus z squared. Now, what about phi? Now, the key thing with phi, and I've drawn this in red because this is the key thing. This angle here is the same as this angle. Okay, now why can we say that? Well, notice that this line here, okay, this vertical line here and this line here, those are parallel lines. And we have this line segment that goes through those 2 parallel lines. So imagine this line segment being part of a line. Okay, and whenever that's the case, okay, if you have 2 parallel lines and another line that intersects through the 2 lines, this angle will be the same as that angle. Okay, so if this is phi, that's phi, and that's just a fact from geometry. Okay, but this phi is really what we're going to use for all these formulas. I've written in red here just to really emphasize this phi. So notice, how can we write phi in terms of r, theta, and z? Well, notice that tangent of phi, so this is part of this triangle here. So I'm not focusing on this phi here, I'm focusing on this one. They're the same thing, but just look at it in this triangle. Tangent of phi is r over z. And notice that's what I've written here, right? Tangent of theta is opposite over adjacent, so it's r over z. So in other words, phi is equal to tangent inverse of r over z. So we've written phi in terms of r and z. Now, I guess technically, okay, tangent of phi is r over z. I guess what would happen if the z were 0? Well, if the z is 0, you're actually down in the xy plane, so what would that phi be? Well, this phi, notice the phi would end up being 90 degrees, right? It'd be pi over 2 radians if z is 0. And actually, if z is negative, the picture gets a little weird, but notice that the phi would be bigger than 90 degrees and less than 180 degrees, right, this phi? And so it'd actually be tangent inverse of r over z plus pi, plus 180 degrees. Okay, but don't worry too much about these technicalities here, but just think of it as tangent of phi is equal to r over z. Okay, now what about the other way around? Suppose we're given the spherical coordinates, rho, theta, phi, and we want to find the cylindrical coordinates, r, theta, z. How do we do that? Well, again, the theta is just the theta. That's easy. Okay, but then notice, look at this angle again here. What's sine of phi? Well, sine of phi is opposite over hypotenuse. It's r over rho. Okay, so if sine of phi is r over rho, multiply both sides by rho, and you'll get r is equal to rho sine phi. So notice we've written r in terms of rho and phi here. Okay, r is equal to rho sine phi. Now we can do the same thing with cosine of phi. Cosine of phi is adjacent over hypotenuse, so it's z over rho. Okay, so in other words, multiply both sides by rho, we would get z is equal to rho cosine phi. And so notice we've written z in terms of rho and phi. Okay, so we have all these coordinates, r, theta, z, in terms of the rho, theta, phi. Okay, so now we know how to convert back and forth between cylindrical and spherical coordinates. Okay, but you see how key this writing this phi here was to all these formulas. Okay, now what about the last case here? How do we convert between rectangular and spherical and rectangular? Okay, so again, from our picture up here, we already know how to do rectangular to cylindrical and back and forth, because that's just like rectangular to polar, essentially, and back. And we just talked about cylindrical to spherical, these two. Now, what about spherical to rectangular and rectangular to spherical? Okay, well, again, we're going to base it on this picture here. Okay, but let's go down. How do we find rho, theta, and phi? Well, remember that r squared is equal to x squared plus y squared, right? That was, in fact, you could look at the picture here. R squared, this thing is the square root of, or r squared will be x squared plus y squared. Okay, again, that really comes from polar coordinates. But then notice also rho squared is equal to r squared plus z squared. So instead of looking at this triangle, look at this triangle. Right, so what's rho squared? Well, it's equal to r squared plus z squared, right, by the Pythagorean theorem. So notice, if rho squared is equal to r squared plus z squared, but r squared is x squared plus y squared, notice what we can do is replace this r squared with x squared plus y squared. Right, because that's what r squared is. So we have x squared plus y squared plus z squared equals rho squared. Or rho is the square root of x squared plus y squared plus z squared. But actually, we kind of already knew that, right? Because how do you locate a point out in 3 space, right? How do you find the distance from that point to the origin, anyway? That would be your rho. Well, the distance from a point x, y, z to the origin, remember, was the square root of x squared plus y squared plus z squared. And that's exactly what we have here. Okay, so we kind of re-derived that. Notice we used the Pythagorean theorem twice to come up with that distance. Okay, now notice we also have cosine of phi is equal to z over rho. Okay, we're using the same thing that we used up here. So again, look at this picture. Cosine of phi is adjacent over hypotenuse, right? So adjacent over hypotenuse is z over rho for this right triangle here. Okay, but then what was rho? Well, rho was the square root of x squared plus y squared plus z squared. So cosine of phi is z over this square root. So phi would be cosine inverse of z over the square root of x squared plus y squared plus z squared. Okay, now finally, tangent of theta is y over x, and again, that comes from the polar coordinates, but notice tangent theta would be opposite over adjacent, y over x. And so theta is tangent inverse of y over x. Now, you do have to be a little careful, and this really just is what you have to be careful with when you're talking about polar coordinates. So you run into an issue if the x is 0, right? So if tangent of theta is y over x, well, what happens if x is 0? Well, notice on this picture here, if we have this point here where the x is 0, so notice that would mean we would be in the YZ plane here, or if we dropped it down to the XY plane, we'd be along the y-axis. Okay, so we're wondering, what is this theta if this point, instead of being out here, if this point is along the y-axis? Well, of course, the theta will be 90 degrees if the y-coordinate is positive. Now, if the y-coordinate were negative, we're back here, your theta would actually be negative 90 degrees. Okay, so if the x is 0, and the y is positive, you get pi over 2 radians. And if x is 0 and the y is negative, you get negative pi over 2. And finally, you run into a little bit of an issue if the theta is bigger than 90 degrees. So basically, if you're over here where the x is negative, and if x is negative, you're on that part of space here, then it turns out you actually have to end up adding pi, so tangent inverse of y over x plus pi. Okay, but again, that's a very technicality type stuff here, so don't worry too much about that. Okay, so that's how we convert from rectangular to spherical. Now, how do we do spherical to rectangular? And by the way, this is the last thing in this video. And I do want you to try these problems from 11.8. So 1a, 3a, 5a, 7a, 9a, and 11a. These are just converting back and forth between these systems. So they'll give you a point in rectangular coordinates, and let's say convert it to spherical coordinates, let's say. Okay, so if we're given rho, theta, and phi, okay, those spherical coordinates, how do we come up with the rectangular coordinates? Okay, x, y, and z. Okay, first of all, let's figure out what z is. Well, notice that cosine of phi, and we've looked at this a couple of times here already, it's z over rho. So look at this, cosine of phi is z over rho. It's adjacent over hypotenuse there. But so in other words, we can write this as z equals rho cosine phi. Okay, so notice we've written z in terms of rho and phi. Okay, now what about y and x? Well, this one you have to be a little clever here. What's sine of phi times sine of theta? Well, sine of phi is opposite over hypotenuse, right? That's r over rho. Okay, we're looking at this triangle. Sine of phi is r over rho. So we've written that right here, r over rho. Now what's sine of theta? Again, don't confuse the phi with the theta. What's sine of theta? Well, sine of theta is opposite over hypotenuse. Okay, so by the way, there's the right angle for this triangle here. But it's opposite over hypotenuse. So sine of phi is y over r. Okay, so notice sine of phi times sine of theta would be r over rho times y over r. So the r's will divide out. And we're just left with y over rho. So in other words, y is equal to rho sine phi sine theta. Okay, so notice we've written y in terms of these three coordinates. We actually had to use all of them, rho, theta, and phi. Okay, and finally, what about the x? Well, this time let's do sine of phi times cosine of theta. Here we did sine of phi times sine theta. Let's do sine of phi times cosine theta. Well, sine of phi again was r over rho. I think I wrote these backwards here. Sine of phi is r over rho. Okay, sine of phi is r over rho. And cosine of theta, so cosine of theta would be x over r. Okay, so I probably wrote these backwards here. So this x over r should be here, and the r over rho should be here. Okay, just to avoid confusion. But the point is, I did this correctly ultimately here. But we divide out these r's, and notice what we get is x over rho. So what is x? Well, x would be, if we multiply both sides by rho, x would be rho sine phi cosine theta. So notice we've written x in terms of rho, theta, and phi. Okay, so that's how you convert back and forth between these coordinate systems. Now you might think, okay, what's the point of all this? Well, in Calculus 4, you're going to do a lot of things where, integration of different surfaces and things in 3 dimensions, where you're going to need to convert back and forth between these different coordinate systems. So sometimes the spherical coordinates will work really well, sometimes cylindrical coordinates, sometimes rectangular, and you need to convert back and forth between these coordinate systems. So this is very important stuff for when you go on into Calculus 4.